Tonight, if you can get far enough from the city lights, look up. There is a faint band of light stretched across the dark, soft as smoke, and for most of human history no one knew what it was. That band is the Milky Way. And here is the strange part. You're not looking at it from the outside, you are inside it. That pale river is the gathered glow of billions of stars in the flat disk of our galaxy, seen edge on, because we live in that disk too. Our sun sits in one long stream of stars and gas we call the Orion Arm. Think of it as our home street in the galaxy. Tonight we're going to walk its true length and its true width, slowly, and ask one simple question. Just how big is the place we live, and why have we never once seen it whole? Go outside on a clear moonless night, far from any town, and let your eyes adjust for a while. After 10 or 15 minutes the sky deepens, and something appears that the city had hidden. A band of pale light, soft and uneven, arcs across the whole sky. It looks like a faint trail of smoke, or like a thin cloud that never moves. People have watched it for as long as there have been people. The ancient Greeks called it a circle of milk. Other cultures saw a road, or a river, or a path for the dead. For thousands of years, no one knew what it truly was. The honest answer waited until the year 1610. That winter, in Padua, an Italian named Galileo Galilei turned a small homemade telescope up toward that band of light. He expected a glowing mist. Instead, he saw stars. Not a few stars, but uncountable stars, packed so densely and so far away that to the naked eye their light blurred together into a single soft glow. The river was not milk and not mist. It was suns. The band you see on a dark night is the combined light of hundreds of billions of stars, too distant to separate, smeared by sheer distance into one pale stripe. Hold that for a moment, because it changes everything that follows. When you look up at that band, you are not looking at a thing in the sky the way you look at the moon, or at a single bright planet. You're looking at the shape of the place you live. That faint river is our galaxy seen from the inside, and the reason it forms a band rather than filling the whole sky is the first real clue to its shape. Think about it gently. If the stars of our galaxy were scattered evenly in a great ball all around us, their combined glow would spread across the entire sky in every direction. But it does not. It gathers into a narrow strip and leaves the rest of the sky comparatively dark. That tells us the stars are not arranged in a ball. They are flattened into a thin sheet, a disk, and we are sitting inside that sheet. When you look along the flat plane of the disk, you look through the most stars, and their light piles up into the band we call the Milky Way. When you look away from that plane, up out of the disk, you look through far fewer stars, and the sky there is dark. So the very first thing the night sky tells you is your own position. You live in a flattened wheel of stars, and the band of light is the rim of that wheel seen edge on from a seat somewhere inside it. That word, inside, is the heart of this whole journey. We have never once stepped outside our galaxy to look back at it. No spacecraft ever will, not in any time scale that means anything to a human life. Every map we have of the Milky Way was drawn from within, by clever people working out the shape of a room they could never leave. And the small region of that room where the sun sits, the long stream of stars and gas we call the Orion Arm, is the place this whole story lives. Tonight we are going to measure it, but first we have to understand exactly what it means to be trapped inside the thing you're trying to see. Imagine you're standing in the middle of a vast, thin crowd. Picture thousands of people spread across an enormous flat field, all roughly at your eye level, stretching away in every direction until they blur into a haze at the horizon. Now look straight up. Above you, there is almost no one, just open sky. Look down past your feet, and again, almost no one. But look out toward the horizon, level with your eyes, and you see person after person after person, overlapping into a dense wall in the distance. That wall is thickest exactly along the flat plane of the crowd. That is what the Milky Way is. You're standing in a flat crowd of stars and the bright band is the crowd seen edgewise. This is the single fact that makes our galaxy so hard to map. We do not get the view from above. We do not get the clean spiral you have seen in pictures, the bright pinwheel with its glowing core and sweeping arms. Those beautiful images are either other galaxies, photographed from outside across millions of light years, or they are artists' impressions, careful guesses built from decades of measurement. We have never had a photograph of our own galaxy from the outside, and we never will. We are inside the crowd. Our galaxy is a barred spiral, a flattened disk of several 100 billion stars with a thicker bulge at the centre and a straight bar of stars cutting across that centre. The whole disk is roughly 100,000 light-years across, but it is thin. If you imagine the galaxy shrunk down to the width of a dinner plate, it would be about as thick as 2 or 3 sheets of paper stacked together. We live deep inside that thin layer, not above it or below it, which is why the band wraps right around our sky in a complete circle. The disk is not empty space between the stars. It is laced with gas and dust, with great clouds of hydrogen and faint soot-like grains, and that dust matters enormously. It blocks visible light. When you look toward the centre of the galaxy, in the direction of the constellation Sagittarius, the band of the Milky Way looks brightest and richest, because that is where the most stars lie. But you cannot actually see the centre with your eyes. The dust in the way absorbs the visible light long before it reaches you. The galactic core is hidden behind a curtain we cannot see through with ordinary eyes. This is why the story of mapping our home took so long, and why it needed more than telescopes that gather light. To see through the dust, astronomers had to learn to listen in radio waves and in infrared, kinds of light that slip past the dust where visible light cannot. Those tools came much later, and we will get to them. For now, settle into the strangeness of the situation. You live in a thin, dusty disk of a few 100 billion stars. You can see the disk all around you as a band of light, but you cannot see its centre, you cannot see its far edge, and you certainly cannot step outside it. Every honest map of the Milky Way is a kind of detective story, pieced together by people who could only measure the things near enough to reach. And so the next question is the obvious one. In this enormous wheel, where exactly do we sit? Let us write down our address in the galaxy, the way you would write a home address on an envelope, working from the largest thing down to the smallest. We live in the Milky Way galaxy. Within it, we live in the flat disk, not the central bulge and not the faint outer halo. Within the disk, we live well out from the centre, in the calm suburbs. And within the suburbs, we live in one particular stream of stars and gas. That is the address we're going to fill in tonight. Start with the most important number. The Sun sits about 26,000 light-years from the centre of the galaxy. That number has been measured many different ways, and the best recent value, from tracking stars that orbit the galaxy's central black hole, lands close to 26,000 light-years. Hold that figure, because it is the anchor for everything else. We're not at the heart of things. We're far out toward the rim, a little more than halfway from the centre to the visible edge. At the very centre of the galaxy lies a supermassive black hole, named Sagittarius A star, with about 4 million times the mass of the Sun. Astronomers tracked individual stars whipping around an invisible point there for nearly 30 years to prove it was real, work that won a Nobel Prize in 2020. But that violent, crowded core is far away from us, 26,000 light-years off, and its light is hidden behind dust. We feel none of its drama. Our corner is quiet. Now, the disk does not just sit still. It turns, like a vast, slow record, and we turn with it. The Sun, carrying the Earth and all the planets, sweeps around the galactic centre at roughly 230 kilometres every second. That is about 500,000 miles an hour. At that speed you could cross the entire United States in under 20 seconds. And yet the galaxy is so unimaginably large that even moving this fast, the Sun takes somewhere between 225 and 250 million years to make one full loop around the centre. One trip around the galaxy is called a galactic year. The last time the Sun was in this exact spot on its orbit, the first dinosaurs were just appearing on Earth, so picture it. We are far out in a turning disk, racing along at 500,000 miles an hour, and still it takes 250 million years to go once around. That is the sheer scale of the place, and the part of the disk we are passing through right now, the local stream of stars and gas that holds the Sun, and every star you can name with your naked eye, is the Orion Arm. It is also called the Local Arm, or sometimes the Orion Spur, and for a long time it was thought to be a small, almost insignificant feature, a minor fragment caught between two grander arms. We now know it is far more substantial than that, but the old name stuck. This is our street. Everything bright in your night sky, every star with a name, the whole of the constellations, all of it lies within the Orion Arm or very close to it. We have not even left the neighbourhood, and we never see it whole. The next thing to understand is why it carries the name of a hunter in the winter sky. The arm we live in is named for a pattern of stars you have almost certainly seen. On a winter evening in the northern hemisphere, or a summer one in the south, one constellation stands out above all others: Orion the Hunter. You can find him by his belt, 3 bright stars in a short, straight, evenly spaced row, unlike anything else in the sky. Above the belt sits a reddish star, Betelgeuse, marking one shoulder. Below it shines a brilliant blue-white star, Rigel, at 1 foot. Hanging beneath the belt is the hunter's sword, and in the middle of that sword is a smudge of light that is not a star at all, but a vast cloud where new stars are being born. Our arm took its name from this constellation, and the reason is straightforward. When early astronomers began tracing the nearby structure of the galaxy, they noticed that many of the bright, hot, young stars and the great glowing gas clouds near us seemed to cluster in the direction of Orion. The Orion Nebula, that smudge in the sword, is one of the closest large stellar nurseries to Earth. So the local feature of the disk, the stream of gas and young stars threading past the Sun, was named for the constellation that marks it most clearly in our sky, the Orion Arm. There is a gentle thing to understand here about constellations. The stars that make up the shape of Orion are not all the same distance from us, and they are not physically grouped together in space. They only look like a single figure because of the chance direction we see them from. Betelgeuse, the red shoulder, lies somewhere around 500 to 600 light-years away. Rigel, the bright foot, is farther, perhaps 860 light-years. The 3 belt stars are farther still, well over 1,000 light-years off, and they are not even quite the same distance from each other. The hunter is a trick of perspective, a pattern our eyes connect across wildly different depths. But that trick points us in a true direction. When you look toward Orion, you are looking along a particularly rich stretch of our own arm, out past the Sun's neighbourhood toward a great complex of gas and newborn stars. The hunter is a signpost. Follow his sword down to that faint smudge, and you are looking at one of the defining landmarks of the very arm we live in. It helps to picture the naming the way you might name a road for the most famous thing on it. Imagine a long street, and on that street stands a single grand cathedral that everyone knows. People begin calling the whole street Cathedral Road, even the parts far from the cathedral, even the houses at the quiet end. The Orion Arm is like that. Orion and its nebula are the cathedral, the unmistakable landmark, and the whole local stream of the galaxy borrowed the name. The Sun itself sits a little inward of the brightest part of this stream, slightly toward the galactic centre from the Orion Nebula. So when you face Orion on a winter night, you are roughly facing outward along our arm, away from the galaxy's core. Turn around toward the constellation Sagittarius and the heart of summer's Milky Way, and you are facing inward, toward the centre. Our arm runs between those directions, and it does not run alone. On either side of us lie 2 more arms, and to understand our place we need to meet the neighbours. Our arm is not the only one. The disk of the galaxy is wound through with several great spiral arms, and the Orion Arm sits between 2 of the largest, like a quiet lane running between 2 major highways. To find our place, it helps to meet the highways first, one on each side. look inward, toward the centre of the galaxy, in the direction of the constellation Sagittarius. Beyond us in that direction lies the Sagittarius Arm, sometimes called the Sagittarius-Carina Arm, because it sweeps through both of those constellations across the sky. It is one of the galaxy's major spiral arms, a long bright lane of stars and gas closer to the centre than we are. When you look at the summer Milky Way at its richest and most crowded, low towards Sagittarius, much of that density is the stars of that inner arm, layered behind the nearer ones. Now look the other way, outward, away from the centre, toward the constellation Perseus. Out there lies the Perseus Arm, another of the galaxy's major arms, farther from the centre than we are. It is one of the most prominent arms in the outer disk. The famous double cluster in Perseus, two glittering knots of young stars that you can glimpse as a faint patch on a dark autumn night, sits out toward that arm. So the Perseus Arm is our outer neighbour, and the Sagittarius Arm is our inner neighbour, and between them runs the Orion Arm. For decades this was the heart of the puzzle. The two flanking arms, Sagittarius and Perseus, are grand, sweeping major features that wrap a long way around the galaxy. Our own arm seemed, by comparison, smaller and shorter, a modest stream caught in the gap between the two big ones. That is why it picked up the dismissive nickname, the Orion Spur. A spur in this sense means a minor branch, a short side feature rather than a true main arm. The picture was of two great arms with a little broken fragment wedged between them, and we happened to live on the fragment. It is worth pausing on how reasonable that idea seemed at the time. From inside the disk, with dust blocking the view, all anyone could measure clearly was the gas and bright stars within a few thousand light years. Trace those nearby, and you find a modest local concentration. The grander arms, glimpsed only in patches through the dust, looked obviously larger, so the local feature was filed away as a minor spur, and that label held for half a century. Picture the layout from above, as best we can reconstruct it. The galaxy turns like a great pinwheel. From the bright central bar, two or more major arms wind outward in a slow curve. The Sagittarius Arm is one lane of that pinwheel, inward of us. The Perseus Arm is another lane, outward of us, and the Orion Arm threads between them, running in roughly the same winding direction, carrying our sun along with it. The gap between us and each neighbour is not small. The distance from the Orion Arm out to the Perseus Arm is something like 6,000 to 7,000 light-years of mostly thinner space. These are not crowded lanes packed end to end. They are broad streams separated by wide, quieter gaps. To feel any of these numbers, though, we first have to nail down the size of our own arm, and that is where the real shock begins, because the Orion Arm turned out to be far larger than anyone expected. Now, we come to the numbers that give this whole journey its name, because the true scale of the Orion Arm is genuinely hard to hold in your head. Let us build it up slowly, one measurement at a time, so that each piece has somewhere to sit. Start with the width of the arm, the distance across it. The Orion Arm is roughly 3,500 light-years wide. That is the thickness of the stream we live in, measured across its narrow direction. Already this is a number with no human handle on it, so let us not pretend otherwise yet. Just hold it. 3,500 light-years across. Now the length. This is the part that changed. For decades the Orion Arm was thought to be short, a stubby spur only a few thousand light-years long, which is why it seemed minor. But in 2013, and then more firmly in 2016, a team of astronomers led by Yeshu and Mark Reid, using precise distances to clouds of gas, found that our arm is far longer than anyone had assumed. They traced it to a length of at least 20,000 light-years, and possibly more. It is not a little spur at all. It is a long, substantial branch, comparable in extent to the major arms it sits beside. The fragment turned out to be a feature stretching a fifth of the way across the entire galaxy. Let that resettle the picture. Our home is not a scrap caught between two grander streets. It is a great winding stream in its own right, 20,000 light-years long and 3,500 light-years wide. carrying the sun and nearly every star you have ever seen with the naked eye. Here is the first real scale shock, and the cleanest way I know to deliver it. Every single star you can see in the night sky without a telescope, every named star in every constellation, the entire familiar sky, lies within the Orion Arm or right at its edges. The farthest naked eye stars are at most a few thousand light years away. The arm is 20,000 light years long, so everything you have ever pointed at, every star anyone before you ever named or wished upon, fits inside a small fraction of just our one arm. The whole human night sky is a single tiny lit corner of one branch of one galaxy. We can sharpen it further. The sun's neighbourhood, the bubble of nearby stars within about 100 light years, contains a few thousand stars. The Orion Arm contains, by rough estimate, millions upon millions of stars across its length and breadth. And the Orion Arm is just one of several arms, and the galaxy is one of perhaps 2 trillion galaxies in the visible universe. But we will not run off into that vastness tonight. The point is the opposite. The point is how enormous our own street is, the one we never leave. You could travel outward from the sun at the speed of light, the fastest anything can go for 20,000 years, and still not reach the far end of our own arm. To make any of this real, we have to do one thing first. We have to understand the unit we keep using, the light year, not as a word, but as a feeling. Because until a light year means something in your body, none of these numbers can land. So let us slow all the way down and take just one light year apart. A light year sounds like a measure of time, and that confuses people, so let us clear it up first. A light year is not an amount of time, it is a distance. It is how far light travels in 1 year. And because light is the fastest thing there is, a light year is an enormous distance. So let us build it from something you can feel. Light moves at about 300,000 kilometers every second. That is roughly 186,000 miles per second. The numbers are too big to feel as written, so anchor them. In 1 second, a beam of light could circle the entire Earth about 7.5 times. In the time it takes you to say the word second, light has gone around the whole planet 7 times over. Now bring it closer to home. The moon is, on average, about 380,000 kilometers away. A beam of light crosses that gap in just over 1 second. When astronauts on the moon spoke with mission control on Earth, there was a small delay in the conversation because their radio signals travelling at the speed of light took more than a second each way. That is the moon. Light. 1 second. Step out to the sun. The sun is about 150 million kilometers away. Light takes a little over 8 minutes to cross that distance. This means the sunlight warming your face left the surface of the sun 8 minutes ago. If the sun were somehow switched off, you would not know for 8 minutes. You're always seeing the sun slightly in the past. That 8-minute distance has its own name, but think of it simply as 8 light minutes. Keep going. Out past all the planets, light takes about 5.5 hours to reach Neptune from the sun. The spacecraft Voyager 1, launched in 1977, and now the most distant human-made object, is so far away that its radio signals take more than 20 hours to reach us, even at the speed of light. And Voyager 1, after almost 50 years of flight, has travelled less than 1/1000th of a single light year. Read that again gently. Our fastest, farthest probe, after half a century, has not crossed even 1,000th of 1 light year. So now you can feel the size of the unit. A light year is the distance light covers in a full year of seconds, each second long enough to lap the Earth 7 times. It comes to about 9.5 trillion kilometers, or nearly 6 trillion miles. Written out, that is a 9 followed by 12 zeros in kilometers. The number is meaningless as digits. What is not meaningless is this. Nothing we have ever built could cross a single light year in less than tens of thousands of years. And our arm is 20,000 light years long. This is the lever that lifts the whole story. When we said the nearest big arm beyond us, the Perseus arm, lies thousands of light years away, we meant thousands of these. When we said the galaxy's centre is 26,000 light-years off, we meant 26,000 of these unthinkable spans, each one a distance our fastest spacecraft could not cross in 500 human lifetimes. So hold the light-year now not as a number, but as a wall, an almost unbridgeable gap. With that wall in mind, the next step becomes astonishing in the other direction, because some stars are close, just a few light-years away, and even those nearest neighbours, the closest suns to our own, are almost impossibly far. With the light-year settled in your bones, let us take a short walk out from the sun and meet the nearest stars. These are our immediate neighbours in the Orion Arm, the closest other suns to our own, and even they will stretch the imagination. The very nearest star system to us is Alpha Centauri, and it sits about 4 1/3 light-years away. You can see it from the southern hemisphere as a single brilliant point, but it is really 3 stars bound together. 2 of them, Alpha Centauri A and B, are sun-like stars circling each other. The third, a small faint red star called Proxima Centauri, is slightly closer to us than the other 2, which is why it holds the title of the closest known star to the Sun, at about 4 1/4 light-years, and Proxima has at least one planet orbiting it, a world named Proxima b, roughly the size of Earth, sitting at a distance where liquid water might be possible. Now feel that distance honestly. 4 1/4 light-years is the closest other star there is. If you shrank the Sun down to the size of a single grain of sand, the Earth would be a speck circling it a few centimetres away, and Proxima Centauri would be another grain of sand placed several kilometres off, with nothing but empty darkness in between. That is the spacing of stars. They are grains of sand kilometres apart, and that is the close one. Remember Voyager 1, our fastest probe, the one that has flown for nearly 50 years. If Voyager 1 were headed toward Proxima Centauri, which it is not, it would take over 70,000 years to get there. 70,000 years to reach the single nearest star. Step a little farther and you reach Barnard's star about 6 light-years away. It is a small, dim red dwarf, far too faint to see with the naked eye, but it is famous among astronomers for moving across our sky faster than any other star, which is how the American astronomer Edward Barnard noticed it in 1916. It is racing through our neighbourhood, and we can watch it shift its position year by year against the more distant stars. A little farther still, about 8.5 light-years away, shines Sirius, the brightest star in the entire night sky. You can find it easily in winter, down and to the left of Orion's belt, blazing white and often flickering through every colour as its light bends through our atmosphere. Sirius looks so bright partly because it is genuinely luminous, about twice the mass of the Sun and far hotter, and partly because at 8.5 light-years it is simply one of our nearer neighbours. It too has a hidden companion, a dense white dwarf called Sirius B, the burnt-out core of a once larger star, packed to the size of the Earth but holding the mass of the Sun. So here is the shape of our immediate neighbourhood. Within about 10 light-years of the Sun, there are only a handful of star systems. You could count the nearest ones on your fingers. The space between stars is mostly emptiness, vast and dark and quiet. And now, hold the 2 scales side by side. The nearest star is 4 light-years away, so far that our fastest probe would need 70,000 years to reach it, and our arm is 20,000 light-years long. The gap to our single closest neighbour is a tiny step across a stream that runs for 20,000 of those steps. Standing inside something that large, how could anyone ever begin to map it? Here is the puzzle at the centre of this whole story, and it is worth feeling fully, because every clever thing that follows is an answer to it. How do you map a structure you can never leave and never see from outside? Picture yourself dropped into the middle of a vast dark forest at night, with only a dim lantern. You cannot fly above the trees, you cannot reach the edge, you cannot even see very far because mist hangs between the trunks and swallows your lantern light after a short distance. And your task is to draw an accurate map of the entire forest, its overall shape, where it thins and where it thickens, the long lanes running through it. That is exactly the position astronomers have always been in with the Milky Way. We are in the forest. We have a dim lantern. There is mist. And we must somehow draw the whole shape. The mist is real. It is the interstellar dust we met earlier, fine grains spread through the gas of the disk, and it blocks visible light. Look toward the crowded centre of the galaxy, and the dust forms dark rifts and lanes, swallowing the light of everything behind them. Invisible light we can only see clearly for a few thousand light-years before the dust draws a curtain. The galaxy is 100,000 light-years across, and our ordinary view reaches only a small bubble within it. Then there is the deeper problem, the one that does not go away even on the clearest night. To map anything, you need to know how far away things are. A point of light in the sky tells you a direction, but not a distance. Two stars can look equally bright, yet one might be a modest star that is close, and the other a brilliant star that is enormously far. Without distance, the sky is flat, a painted ceiling. You cannot build a map of a room from a flat painting of one wall. You need depth, and depth, for the stars, is the single hardest thing to measure. So the entire history of mapping our galaxy is really the history of finding ways to measure distance, again and again, with cleverer and cleverer methods, each one reaching a little farther into the mist. Every breakthrough in this story is, at heart, a new way to answer the question, how far? And there is one more twist that makes it harder still. We're not only inside the forest, we're not even at its centre, which we might at least have guessed at. For a long time, people assumed the sun sat near the middle of everything, because from inside the band of the Milky Way looks roughly even all the way around. If you're off to one side of a great even crowd, you might still feel central, because the crowd surrounds you on every side. So our first instinct was the natural human one. We placed ourselves at the heart of things. That instinct was wrong, and discovering how wrong it was became one of the great humblings in the history of science. We're not at the centre. We're far out toward the rim, in the quiet suburbs, on an arm we long mistook for a minor spur. But to get there, to that humbling and that map, someone first had to try. And the first person to truly attempt it, to count the stars and reason out the shape of the whole galaxy from inside, was a musician turned astronomer, working with his sister and a homemade telescope in England more than 200 years ago. The first serious attempt to map the shape of our galaxy was made by a man who began his life as a musician. William Herschel was born in Germany in 1738 and moved to England, where he made his living as an organist and composer in the city of Bath. Astronomy was his passion, pursued at night, and he built his own telescopes, grinding the mirrors by hand, with his sister Caroline Herschel working alongside him as his tireless assistant, and a remarkable astronomer in her own right. Together they built some of the finest telescopes in the world. Herschel had a bold idea. He could not see the whole galaxy, but perhaps he could measure its shape by counting. The plan was simple to state and exhausting to carry out. He would point his telescope at many different patches of sky, all around the heavens, and in each patch he would count how many stars he could see. He called this star gauging. The reasoning ran like this. If our system of stars had an edge, then looking in the directions where the system was deep, he would see many stars stacked up, and looking where it was shallow, he would see few. By comparing the counts in every direction, he could work out the rough shape of the whole. In 1785, Herschel published his result. He had counted stars across the sky and assembled for the first time a reasoned diagram of the Milky Way's shape. His map showed a flattened, raggedy shape, longer in some directions than others, with the sun sitting somewhere near the middle. It was the first time anyone had drawn the galaxy as a structure with a form, rather than just describing the band of light. It was a genuine landmark in human understanding. But it was wrong in two important ways, and the reasons are worth understanding because they show exactly how hard this problem is. The first mistake was the dust. Herschel did not know it was there. He assumed that when his counts ran out, when he stopped seeing more stars in a given direction, it meant he had reached the edge of the star system. But often he had simply reached the limit of what the dust would let through. The mist in the forest was stopping his lantern light, and he read that as the forest ending. Where the dust was thick, the galaxy looked shallow, when really it ran on far beyond. The second mistake was placing the sun in the middle. Herschel had to assume that all stars were about equally bright, so that fainter ones were simply farther away. With that assumption, the even spread of stars around the sky put us near the centre. But stars are not all equally bright, and we are not near the centre. The even-looking band fooled him, just as it would fool others for over a century more, and yet none of this diminishes what he did. Herschel took the impossible problem, mapping a structure from inside, and made the first real attempt with the only tool he had, patient counting. He also discovered the planet Uranus, catalogued thousands of faint smudges that later turned out to be other galaxies, and even discovered infrared light. He and Caroline pushed human sight outward farther than anyone before them. It would take a different kind of measurement, and another bold astronomer more than a century later, to move the sun out of the centre and show us where we truly stand. His name was Harlow Shapley, and his clue came from great glowing balls of ancient stars. For more than a century after Herschel, most astronomers still placed the sun at or near the centre of the galaxy. It was a comfortable idea, and the even band of the Milky Way seemed to support it. The man who overturned it was an American astronomer named Harlow Shapley, working in the 1910s at the Mount Wilson Observatory in California, where he had access to what was then one of the largest telescopes in the world. Shapley was not studying the disk. He was studying globular clusters. A globular cluster is a tight, roughly spherical swarm of very old stars, hundreds of thousands of them packed into a ball, bound together by their own gravity. There are around 150 of these clusters associated with our galaxy. Through a telescope they look like glittering fuzzy spheres, and they are some of the oldest things in the Milky Way, many of them around 12 or 13 billion years old, nearly as old as the universe itself. Shapley realised something crucial about where these clusters sit. They do not lie flat in the disk with everything else. They form a great spherical halo spread out in a huge ball around the galaxy. And here was his key insight. If the clusters are arranged in a ball, then the centre of that ball should mark the centre of the galaxy. Find the middle of the swarm of clusters, and you have found the heart of the whole system. So Shapley needed to measure the distances to the globular clusters. To do it, he used a remarkable kind of star called a variable star, one that pulses, growing brighter and dimmer in a steady rhythm. A few years earlier, an American astronomer named Henrietta Swan Leavitt had discovered that for one type of these pulsing stars, the rhythm of the pulsing reveals the star's true brightness. A slow pulse means a brighter star, a fast pulse a fainter one, and once you know a star's true brightness and compare it to how bright it looks, you can work out how far away it must be. Leavitt's discovery handed astronomers a measuring stick that reached across enormous distances. It is one of the most important tools in the history of the science. Shapley used that measuring stick on the variable stars in the globular clusters, and he mapped the three-dimensional positions of the clusters around the galaxy. When he found the centre of their great spherical swarm, he got a shock. The centre was not near the sun at all. It lay far off, tens of thousands of light years away, in the direction of the constellation Sagittarius. The clusters were not centred on us. They were centred somewhere else entirely. The conclusion was unavoidable, and it was a profound humbling. The sun is not at the centre of the galaxy. We sit far out toward the edge, in the quiet outskirts, with the true heart of the Milky Way lying thousands of light years away behind the dust of Sagittarius. Shapley had moved us off the centre of the map, just as, centuries earlier, others had moved the Earth off the centre of the solar system. His exact numbers were not perfect, because he too did not fully account for the dimming effect of dust, and he overestimated the size of things. But the great conclusion was right and has never been overturned. We live in the suburbs, and once astronomers accepted that, the next task became urgent and clear. If we are out on the rim, in an arm, then where exactly do the arms lie? To trace them through the dust, someone would have to find a way to see what visible light could not reach. The answer came from hydrogen and from a faint whisper in radio. To map the spiral arms, astronomers needed to see through the dust, and visible light simply could not do it. The breakthrough came from the most common substance in the universe, hydrogen gas, and from a kind of light our eyes cannot see at all, radio waves. The space between the stars is not empty. It is filled, thinly, with gas, and most of that gas is hydrogen, the simplest atom there is, a single proton with a single electron. There is a vast amount of it spread through the disk of the galaxy, far more than is locked up in the stars, and in 1944, a young Dutch astronomer named Hendrik van der Hulst predicted something remarkable about this cold hydrogen gas. He calculated that, very rarely, a hydrogen atom would flip a tiny internal switch, and in doing so would give off a faint pulse of radio energy at one exact wavelength, 21 centimeters. About the width of this is the length of your forearm from elbow to wrist. For any single atom, this flip is extraordinarily rare, happening on average only once in millions of years. But there is so much hydrogen in the galaxy, in such enormous clouds, that across all those countless atoms, the faint 21 centimeter signal adds up into a steady whisper that fills the sky. And crucially, radio waves at this wavelength sail straight through the dust that blocks visible light. The mist in the forest is invisible to them. For the first time, astronomers had a way to map the gas of the entire galaxy, dust and all. The prediction was confirmed in 1951, detected by teams working in the United States and the Netherlands within weeks of each other. And then the real work began. Radio astronomers began scanning the sky, listening for the 21 centimeter whisper, mapping where the hydrogen lay. Here is the elegant part, the trick that turned the whisper into a map with depth. The galaxy is turning, and different parts of it move toward us or away from us at different speeds. When a source of waves moves toward you, its waves get slightly squeezed. When it moves away, they get slightly stretched. You have heard this with sound, in the way a passing siren drops in pitch as it goes by. The same thing happens to the hydrogen signal. Clouds moving at different speeds show the 21 centimeter line shifted by slightly different amounts. By measuring those shifts, astronomers could work out how fast each cloud of hydrogen was moving, and from its motion, estimate roughly how far away it lay along the line of sight. It was the first tool that gave real depth to the map. By the 1950s, radio surveys had begun to reveal long, curving concentrations of hydrogen gas threading through the disk. These were the spiral arms, traced not by starlight, but by the cold gas between the stars glowing faintly in radio. For the first time, the arms of the Milky Way appeared on a map drawn from inside. The picture was rough. The distances from this method were uncertain, because the gas does not move in perfectly simple circles, and a cloud's speed does not pin down its distance exactly. But it was a true beginning. The Sagittarius Arm, the Perseus Arm, and the local concentration around Orion all began to take shape in the radio maps. Hydrogen gave us the bones of the galaxy, but to firm up the arms and see them sharply, astronomers would also turn to the brightest, most short-lived stars in the sky, beacons that mark exactly where arms are being born. Alongside the radio maps of hydrogen, astronomers had another way to trace the spiral arms, this time using visible light after all, but only a very particular kind of star. To understand it, you need to know one thing about how stars live and die, because it turns certain stars into perfect signposts. Stars come in a great range of sizes and temperatures, and they do not all live the same length of time. The most massive stars, the giants that burn blue-white and ferociously hot, are spendthrifts. They are dozens of times the mass of the Sun, and they pour out their energy so fast that they burn through their fuel in only a few million years before exploding. Astronomers label these hot, massive stars with the letters O and B. the two hottest categories, and so they are often called OB stars. They are rare, they are blindingly luminous, and above all, they do not last long. That short life is exactly what makes them useful. A star that lives only a few million years cannot travel far from its birthplace before it dies. A few million years sounds long, but on the scale of the galaxy, it is the blink of an eye, far too short for a star to drift away from the gas cloud that made it. So wherever you find these brilliant OB stars, you are looking at a place where stars have very recently been born, and stars are born in the spiral arms, where the gas piles up thick enough to collapse into new suns. The OB stars light up the arms like fresh paint, marking exactly where the action is right now. So astronomers began mapping the positions of the brightest, hottest, youngest stars, and the great glowing clouds of gas lit up around them, called emission nebulae. These hot young stars and their glowing nurseries traced the nearby spiral arms in visible light, picking out the lanes where new stars are forming. The Orion Nebula, that smudge in the hunter's sword, is exactly this kind of marker, a nursery full of brilliant young stars lighting up the gas around them, sitting in our own arm. In the 1950s, an American astronomer named William Morgan and his colleagues mapped the distances to many of these hot young stars and their clusters in the Sun's neighbourhood. When they plotted the results, the stars did not scatter randomly. They fell into curving lanes. Morgan presented the first optical evidence of spiral arms near the Sun, and the audience of astronomers reportedly broke into applause, because here, at last, were the arms made visible, drawn from the positions of stars we could actually see. But this method too had a hard limit. The very dust that blocks our view also dims and reddens the light of these stars, making their distances tricky to pin down. And it only works where we can see the stars at all, within a few thousand light years before the dust closes in. The hot stars sharpened the picture of the nearby arms, especially our own, but they could not reach across the whole galaxy. So by the second half of the 20th century, astronomers had two complementary tools. Radiohydrogen gave the broad bones across great distances but with fuzzy depth. Hot young stars gave sharp, vivid markers nearby but only in a limited bubble. Both pointed to the arms, and both agreed our local stream around Orion was real. What was still missing was a way to measure distances directly, cleanly, without guessing from brightness or motion. That clean method is the oldest idea in the book, and only recently has it been pushed to its full astonishing power. The cleanest way to measure the distance to a star is also the oldest, and you can demonstrate the whole principle right now with nothing but your own hand. Hold one finger up at arm's length, close your left eye and look at it with just your right. Now switch. Close your right eye and look with just your left. Your finger appears to jump sideways against the background of the room. Nothing moved but your viewpoint. That apparent shift, caused by looking from two different positions, is called parallax, and the closer your finger is to your face, the bigger the jump. Bring it close to your nose and it leaps wildly. Hold it far away and it barely shifts. Stars do exactly the same thing if you have a wide enough pair of eyes. As the Earth travels around the Sun across a year, our viewpoint swings from one side of the Sun's orbit to the other, a baseline of about 300 million kilometers. From these two extreme positions, 6 months apart, a nearby star appears to shift its position very slightly against the far more distant background stars. Measure that tiny shift, know the size of the Earth's orbit, and simple geometry gives you the distance. No assumptions about brightness, no guessing from motion, just the angle and a triangle. It is the gold standard of distance measurement, the one against which all others are checked. The catch is that the shift is breathtakingly small. Even for the nearest stars, it is a tiny fraction of the width of a hair held at arm's length. The first time anyone succeeded in measuring a stellar parallax was 1838, when the German astronomer Friedrich Bessel measured the distance to a star called 61 Cygni. It was a triumph, but from the ground, blurred by our restless atmosphere, parallax could only reach the closest stars, a small bubble around the Sun. The method was clean but short-sighted. The way to extend it was to leave the atmosphere behind and measure from space with extraordinary precision. The European Space Agency launched a first mission for this, called Hipparcos, in 1989, but the Great Leap came with its successor. In 2013, the European Space Agency launched a spacecraft called Gaia, and Gaia has rewritten our map of the galaxy. Gaia's task is staggering in its simplicity and its scale. It sits far from Earth, beyond the Moon, slowly spinning, and it measures the precise position of star after star, over and over, year after year. By tracking how each star's apparent position wobbles as the Earth, and Gaia with it swings around the Sun, it measures parallax for not a handful of stars, but for well over 1 billion of them. Gaia has measured accurate distances to more than 1 billion stars, building the most detailed three-dimensional map of the Milky Way ever made. For the first time, we're not guessing the depth of the nearby galaxy. We're measuring it directly, star by star, by the millions. The fuzzy maps drawn from hydrogen motions and uncertain brightnesses have been replaced near the Sun by a true three-dimensional chart with real distances. Gaia turned the painted ceiling into a room with genuine depth. And yet even Gaia has a limit. Its precise parallaxes reach clearly across thousands of light years. But for the farthest dust-shrouded reaches of the arms, even Gaia's measurements grow uncertain. To pin down the full length of our arm, astronomers needed one more trick, a way to measure distances across the entire galaxy with almost unbelievable precision. That trick listens to natural radio beacons buried inside the star-forming clouds themselves. To measure the most distant parts of our arm, across tens of thousands of light years and right through the dust, astronomers turn to one of the most precise techniques in all of science, and to a strange natural phenomenon hiding inside the clouds where stars are born. Start with the phenomenon. In certain dense, cool clouds of gas, particularly in the regions where new stars are forming, the molecules of water and of methanol can be energized in just the right way to produce an intense, concentrated beam of microwave radio energy, all at a single sharp wavelength. This is a natural version of what a laser does with visible light, except it happens with microwaves rather than light, so it is called a maser. These cosmic masers are tiny, brilliant points of radio brightness, beacons embedded right inside the star-forming regions that mark the spiral arms. Because they are so bright and so sharp, and because radio passes freely through dust, they can be seen clear across the galaxy. Now the technique, which is where the real magic lies. To measure the parallax of these masers, the tiny yearly wobble that gives their distance, astronomers needed sharper vision than any single telescope on Earth could provide. So they combined many radio telescopes, spread across thousands of kilometers, and linked their signals together so that they worked as one. This is called very long baseline interferometry, and the idea is that a set of telescopes scattered across a continent can, in effect, act like a single telescope as wide as the distance between them. The wider the spread, the sharper the vision. Spread your telescopes across the United States, and you get a radio eye thousands of kilometers across. With this continent-sized radio eye, astronomers could measure the positions of the masers with almost incomprehensible precision, fine enough to detect the minuscule parallax wobble of a beacon tens of thousands of light years away. The great project that did this is called the BeSSeL Survey, short for the Bar and Spiral Structure Legacy Survey, led for years by the American astronomer Mark Reid and an international team using a network of radio dishes called the Very Long Baseline Array. They spent years measuring the precise distances and motions of hundreds of these water and methanol masers scattered through the star-forming regions of the galaxy. The result was the most accurate map ever made of the spiral arms of the Milky Way, with real, directly measured distances reaching across the disk and through the dust that had blocked every earlier attempt. Where Herschel had counted, where radio had listened to hydrogen, where Gaia measured the nearby millions, The massa parallaxes finally pinned down the far structure of the arms with geometry as clean as that finger held at arm's length, only stretched across the entire galaxy. And it was this survey, more than any other single effort, that delivered the great surprise of our story. Because when Mark Reid, Ye Shu, and their colleagues plotted the masses belonging to our own local stream, the Orion Arm, the points did not trace a short, stubby spur caught between two grander arms. They traced something far longer and far more substantial, running on and on through the disk. The minor spur, it turned out, was nothing of the kind. The very tools built to map the grand arms had quietly revealed that our own arm was grander than anyone had let themselves believe. To see how that discovery unfolded, we need to watch the Orion spur grow up. For more than half a century, the textbooks were consistent and confident on one point. Our local stream of stars and gas, the Orion Arm, was a minor feature. It was called the Orion spur, and the word spur did real work. It told you not to take it too seriously. The galaxy had its grand spiral arms, the Sagittarius Arm and the Perseus Arm and others, sweeping in long majestic curves, and then there was our little spur, a short broken segment wedged in the gap between two of them, where the sun happened to live. We were on the scrap, not the structure. The reason for this modest picture was simple. From inside the dust, with only the old tools, no one could trace our local feature very far. Radiohydrogen showed it as a smallish concentration. The hot young stars marked it clearly, but only nearby. Everything that could be measured suggested a short, stubby thing, perhaps a few thousand light-years long, so a short, stubby thing it was assumed to be. Then came the massa parallaxes, the continent-sized radio eye measuring true distances clear across the galaxy. And in 2013, a team led by Ye Shu, working with Mark Reid and others on the BeSSeL Survey, published a result about our own arm that quietly upended the textbook. They had measured the precise distances and motions of the star-forming masas belonging to the local arm, our arm, and the picture that emerged was completely unexpected. The Orion Arm was not short. It was not a stubby fragment. The masas traced a long, substantial structure, comparable in its star-forming richness and its extent to the major arms it sat beside. The team found that the local arm was much larger than previously thought, with dimensions and a density of young stars putting it on a similar footing to its grand neighbours. By their later work in 2016, the traced length had grown to something like 20,000 light-years, a major branch of the galaxy in its own right. Think about what that means as a human story, not just a scientific one. For 50 years we had a slightly diminished view of our own address. We lived, we thought, in a galactic backwater, a minor spur, easy to overlook. And then better instruments did not just refine that picture, they overturned it. The very arm we live in, the one carrying every star you've ever seen, turned out to be far grander than we had given it credit for. The neighbourhood we thought was a side lane was a great avenue all along. We had simply been unable to see far enough down it. There is a lesson in that worth holding on to on a calm night. The limits of a map are often the limits of the tools, not the limits of the thing being mapped. Herschel's galaxy stopped where the dust stopped his lantern, not where the stars stopped. Shapley's sun sat at the centre only until better measurements moved it out, and our arm stayed a minor spur only until a continent-sized radio eye could follow it to its true length. Each time, the universe turned out to be larger and richer than the previous map allowed, so the name lingers, the Orion spur, out of habit, but the better name is the local arm, and it is no spur, it is a long, bright branch of the Milky Way, and we ride along it. But naming it raises a deeper question we've been circling all along. What actually is a spiral arm? Is it a solid thing, a fixed stream of particular stars, or is it something stranger? To understand where we live, we now have to understand what an arm truly is. We have spent this whole journey so far talking about the Orion Arm as a place, a stream of stars and gas where the sun lives, but now we reach a question that sounds simple and turns out to be deep. What actually is a spiral arm? Is it a fixed collection of stars, like a particular crowd of people who always travel together? Or is it something else entirely, something that only looks solid from a distance? Start with the picture most people carry in their heads, because it is wrong, and seeing why is the key to everything. Most of us imagine a spiral galaxy as a kind of solid pinwheel. The arms are made of certain stars, and as the galaxy turns, those arms sweep around like the spokes of a wheel or the arms of a spinning fan, keeping their shape, carrying the same stars around and around. It is a natural image. It is also impossible, and a moment's thought shows why. The galaxy does not turn like a solid wheel. The stars near the centre complete their orbits much faster than the stars far out near the rim, because that is how gravity works around a concentrated mass, just as the inner planets orbit the Sun faster than the outer ones. So if the arms were fixed lines of particular stars, the galaxy's faster inner parts would race ahead of its slower outer parts, and within just a few turns the arms would wind up tighter and tighter, like cream stirred into coffee, until they smeared away into nothing. This is called the winding problem, and it has troubled astronomers since the arms were first understood. Galaxies are billions of years old. They have turned dozens of times, yet their arms are still open and graceful, not wound into a featureless blur. So the arms cannot simply be fixed streams of the same stars going around together. Something else must be happening. That something else is the central idea we will open up next, but here we can name the puzzle clearly because it reframes our whole address. The question of whether the Orion feature is an arm or merely a spur is, in part, a question about what arms are made of and how they hold their shape. If an arm is not a fixed group of stars, then what is it that we are riding inside? What is the thing called the Orion Arm, if not the particular stars around us? Here is a first gentle hint to carry into the next chapter. Think of the stars and gas of the disk as a great flow of traffic on an enormous circular road, all moving along, all orbiting the centre. Now imagine that somewhere on that road, for some reason, the traffic bunches up, slows, and crowds together. The way cars pile up at a busy stretch of highway. The individual cars keep moving through the jam, entering it, slowing within it, and eventually passing out the far side. But the jam itself, the region of crowding, can stay in roughly the same place, or drift slowly, even as the cars pour through it. The pile-up is real, you can see it, you can map it, but it is not made of any fixed set of cars. It is a pattern, and the cars are just passing through. A spiral arm may be much more like that traffic jam than like a solid spoke. The stars are the cars. They flow through the arm and out the other side, while the arm itself, the region of crowding, persists. If that is true, then the Orion Arm is not so much a fixed place as a slow-moving wave that the Sun is passing through. And that idea, that the arms are waves, changes how we picture our home completely. We ended the last chapter with a picture worth holding on to. A spiral arm may be less like a solid spoke and more like a traffic jam, a region of crowding that stays in place while the cars pour through it. This idea has a name. It is called density wave theory, and it was worked out in the 1960s, most fully by two scientists working in the United States, Chia Chiao-Lin and Frank Xu. It is still our best explanation for how spiral arms hold their graceful shape over billions of years, and it changes what it means to live in the Orion Arm. Here is the idea, built up gently. Imagine all the stars and gas of the disk orbiting the centre, each on its own slow path. Now suppose that, instead of being spread out perfectly evenly, the material is slightly crowded into a spiral-shaped pattern, a wave of higher density winding through the disk. A star orbiting the galaxy will, over time, drift into one of these crowded regions, slow down a little as the extra gravity tugs at it, linger there a while, and then move on out the other side. Stars are always entering the wave and leaving it. The wave itself, the pattern of crowding, turns around the galaxy at its own steady rate, slower than the stars in most places. So the arm is a standing pattern that the stars pass through, not a fixed bundle of stars. This solves the winding problem we met before. Because the arm is a pattern and not a fixed set of stars, it does not wind up as the disk turns. The pattern can keep its open spiral shape for billions of years, even though no single star stays inside it for long. The cars come and go, the jam endures, and the crowding does real work. When gas drifts into the density wave and bunches up, it gets squeezed, and squeezing gas is exactly what triggers it to collapse into new stars. This is why the spiral arms glow. The arms are where the gas piles up, so the arms are where new stars are born, and the brightest, hottest, shortest lived of those new stars light up the arm before they die, while they are still inside it. The arms look bright not because they hold more stars overall, but because they hold the youngest, most brilliant ones freshly made in the crowding. Now bring it home. If the Orion Arm is a density wave, then the Sun is a car passing through it, not a permanent resident. The particular gas and bright young stars that define our arm today are not the Sun's lifelong companions. They are simply the crowd we happen to be among right now, on this stretch of our long orbit. Over the great spans of galactic time, the Sun drifts into arms and out of them, and the arm we call home is the one we are crossing at this moment in cosmic history. It is worth saying that density wave theory is not the whole story, and astronomers still debate the details. Some spiral arms, especially the more ragged, patchy ones, may form in other ways, stirred up by gravity and star formation in a more chaotic, shorter-lived fashion. The Milky Way's arms may be a blend of both. The science here is genuinely unsettled, and that is honest to admit. But the core insight holds, and it reshapes our address. We do not live on a fixed street. We are passing through a slow wave of light. And right around us, inside that wave, sit some of the most interesting structures of all, beginning with a great bubble of near emptiness that the Sun is sitting inside this very moment. Here is something that sounds made up but is not. The Sun right now sits inside a great bubble of near emptiness, a cavity blown clear through the gas of our arm. It is called the local bubble, and our whole solar system has been travelling through it for ages. To picture our true surroundings, you have to start with this hollow we live in. The space between the stars is not uniform. In some places the gas is relatively dense and cold, gathering into clouds. In other places it is thin and hot, blown clear by violent events. The region immediately around the Sun is one of the thin, hot places. For roughly 300 light-years in most directions, the gas around us is far sparser than average, hotter than average, and swept unusually clean. We're inside a low-density cavity, an enormous bubble carved out of the surrounding gas of the Orion Arm. How do you blow a bubble 300 light-years across in the gas between the stars? You need something tremendously violent, and the answer is supernova, the explosions of dying massive stars. When one of those brilliant short-lived O and B stars reaches the end of its few million years, it detonates, briefly outshining a whole galaxy and hurling its outer layers outward at enormous speed. A single supernova sends a shock wave sweeping through the surrounding gas, pushing it back, heating it, clearing a growing cavity. And massive stars are usually born in groups, so they tend to explode in sequence, one after another over a few million years, each explosion pushing the bubble wall farther out. For years this was the leading explanation, but the details stayed fuzzy. Then, in 2022, a team of astronomers led by Catherine Zucker and Alyssa Goodman, using the precise three-dimensional positions from the Gaia spacecraft, reconstructed the story in remarkable detail. They found that the local bubble was carved by a series of supernovae beginning around 14 million years ago, perhaps 15 explosions in all. And they found something lovely. The expanding wall of the bubble, the gas swept up and piled at its edges, is exactly where almost all the nearby young stars and star-forming clouds now sit. The bubble did not just clear a space, its growing wall gathered gas and triggered the birth of the new stars around us. We live in the hollow, and the nurseries sit on the shell. The Sun's place in this is a matter of chance and timing. We did not form in this bubble. The Sun, on its long orbit, simply drifted into the cavity a few million years ago, and we happen to be passing through it now, fairly near its centre. In a sense, we are tourists inside a blast cavity carved by stars that died before our ancestors walked upright. There is a calm beauty to this. The thinness of the gas around us, the clarity of our local space, is the lingering echo of ancient explosions, smoothed now into a quiet hollow. The violence is long past. What remains is stillness, a swept clean room with newborn stars glowing on its distant walls. But the bubble is not perfectly empty. Drifting through it, and drifting through us, are a few wisps of thicker gas, small clouds that survived the clearing. The Sun is passing through one of them right now, a little cloud so close and so present that it touches the edge of the solar system itself. It has a wonderfully plain name, the Local Fluff. Inside the great swept hollow of the local bubble, the gas is not perfectly empty everywhere. Here and there, small wisps of slightly denser gas drift through the cavity, leftover shreds that survived the clearing. And the Sun, at this moment in its long journey, is passing directly through one of these wisps. It has a name that astronomers use with a straight face. It is called the Local Fluff, or more formally the Local Interstellar Cloud. The Local Fluff is small and thin, but it is the gas we are actually immersed in right now. It is a cloud of warm, partly charged hydrogen and helium, stretching perhaps 30 light-years across, and the solar system has been travelling inside it for something like the last few tens of thousands of years. The Sun is moving through this cloud at roughly 25 kilometers per second relative to the gas, which sounds fast and is, but the cloud is so vast that we will take many more thousands of years to cross all the way through it and out the far side. You might ask how a cloud of gas can reach the Sun without simply falling in or being swept away. The answer brings in something we rarely think about: the Sun's own protective bubble. The Sun does not just give off light, it constantly blows out a thin stream of charged particles in every direction, called the solar wind, and that wind inflates a vast protective bubble around the entire solar system, far beyond the planets. This bubble is called the heliosphere, and it acts like a shield, holding the surrounding interstellar gas at bay. The pressure of the solar wind pushing outward balances against the pressure of the local fluff pushing inward, and where they meet, far past the orbit of Neptune, is the true outer boundary of the solar system. We have actually touched that boundary. The two Voyager spacecraft, launched in 1977, travelled outward for decades, and one after the other they crossed the edge of the heliosphere and passed into the interstellar gas beyond. Voyager 1 crossed in 2012, and Voyager 2 in 2018. When they crossed, their instruments measured the change directly, a jump in the density of charged particles as they left the Sun's bubble and entered the thin gas of the local fluff itself. For the first time, human-made objects had sampled the interstellar medium, the actual cloud our solar system is sailing through. They're out there still, beyond the shield, drifting in the gas between the stars. It is worth holding the scale of all this gently. The local fluff is thin, almost beyond imagining, far emptier than any vacuum we can make on Earth. If you could scoop up a handful of it, you would find only a few atoms in a space the size of a small room. And yet, spread across 30 light-years, even that whisper of gas is the medium we travel through, the weather of our little corner of the arm. So our true address grows more precise and stranger the closer we look. We live in the disk of the galaxy, far out toward the rim, on a great branch called the Orion Arm, inside a hollow called the local bubble blown by ancient supernovae, immersed at this moment in a thin wisp called the local fluff, wrapped inside the Sun's own protective heliosphere, layer upon layer, each one moving, each one passing. And just beyond these immediate surroundings lies a larger structure, a great tilted ring of young stars and nurseries that wraps right around our patch of sky. If you trace the brightest, youngest stars in our night sky, the brilliant blue beacons and the great glowing nurseries, you find that they are not scattered randomly around us. They seem to lie along a great circle, a ring of young stars and gas tilted at an angle to the flat plane of the Milky Way. This tilted ring has a name. It is called the Gould Belt, after the American astronomer Benjamin Gould, who described it in the 1870s, though others had noticed the pattern even earlier. Here is what makes it strange and beautiful. Most of the galaxy's young stars and star-forming regions lie close to the flat plane of the disk, in the thin sheet we live inside. But the Gould Belt is tilted, leaning about 20 degrees out of that plane, like a ring set at a slant inside a flatter disk. Many of the most famous bright stars and nurseries near us sit along this tilted ring. The Orion Nebula is part of it. So are the bright young stars of the constellation Scorpius and the nearby star-forming clouds, and many of the brilliant blue stars that decorate our sky. The belt is a great loop of recent starbirth, perhaps 3,000 light-years across, draped around the Sun's neighbourhood at a tilt. For a long time, the Gould Belt was treated as a real, distinct structure, and astronomers wondered what could have made such a tilted ring. Perhaps a great cloud of gas had been struck from outside, or compressed by some passing disturbance, tilting it as it collapsed into stars. It was one of the puzzles of our local neighbourhood, a feature we could see clearly but could not fully explain. And then, as so often in this story, better data changed the picture. When the Gaia spacecraft measured the precise three-dimensional positions of the young stars and clouds around us, astronomers could finally see how this nearby material is really arranged, not as a flat pattern projected on the sky, but in true depth. And what they found, in the years around 2020, was that the old idea of a single neat tilted ring was too simple. The nearby star-forming clouds are arranged in a more complex way than a clean belt, woven into larger structures that the flat view had blurred together. This is a gentle and recurring lesson, worth letting settle. The Gould Belt was a pattern drawn from a flat sky, from directions without true depth. It captured something real, that the young stars near us are concentrated and tilted, but it mistook the full shape, because we were seeing a three-dimensional thing painted onto 2 dimensions. Give us real distances, and the apparent ring resolves into something richer and stranger. The young stars and clouds the Gould Belt traced are genuinely there, genuinely concentrated near us, genuinely tilted from the plane. They are the nearby face of star formation in our arm, the nurseries on our doorstep. What changed is our understanding of how they connect, and when astronomers followed those connections with Gaia's new depth, they found that the nearby clouds are not a simple ring at all, but part of an enormous wave, a long undulating chain of gas and nurseries running for thousands of light years through our arm. It was discovered in 2020. It is one of the largest structures known in our galactic neighbourhood, and almost no one had suspected it was there. It is called the Radcliffe Wave. In 2020, astronomers announced the discovery of something enormous sitting right in our galactic backyard, a structure so large and so close that it is almost embarrassing we had not seen it before. It is a vast wave of gas and young stars, running for about 9,000 light-years through our arm, and it had been hiding in plain sight disguised by our lack of depth perception. It is called the Radcliffe Wave, named for the Radcliffe Institute at Harvard University, where the team that found it worked. The discovery came directly from the new 3-dimensional maps built with the Gaia spacecraft. A team led by Catherine Zucker, João Alves, Alyssa Goodman, and their colleagues took the precise distances Gaia had measured to thousands of nearby star-forming clouds, the great cradles of gas where new stars are born, and they plotted those clouds in true 3 dimensions. Many of these were the very clouds that had been lumped into the old idea of the Gould Belt. But seen in real depth, they did not form a tilted ring. They formed a long, thin, coherent line, a chain of star-forming clouds stretching across 9,000 light-years of our arm. And that line was not flat, it rippled. That is the astonishing part. The chain of gas clouds rises above the flat plane of the galaxy, and then dips below it, then rises again in a long, gentle, regular undulation, like a wave frozen on the surface of a vast lake. The nearest part of this wave passes within about 400 light-years of the Sun. We are not on the wave, but we are very near it, looking at it almost edge-on, which is part of why it had been so hard to recognise. Strung out along it are some of the most famous star-forming regions of our sky, the great nurseries of the Orion Arm, all part of one connected structure that no one had known was a single thing. Why the gas should be arranged in such a clean, rippling wave is still an open question, and astronomers are honest about that. Something must have set the gas oscillating up and down through the plane of the disk, like a rope flicked at one end. Perhaps a smaller galaxy or a clump of dark matter passed through our disk long ago and left this ripple behind. Perhaps it formed from some instability in the gas itself. We do not yet know. The wave may even be slowly moving, with the gas sloshing through the plane over tens of millions of years. These are questions being actively studied right now, with the answers still uncertain. What is not uncertain is that the wave is real, and that it reorganises our picture of home. The nearby nurseries we thought formed a tilted ring are instead beads on a single immense rippling thread, the largest coherent structure of gas yet found near the Sun. It is a reminder of how recently our true neighbourhood came into focus. The Radcliffe Wave was discovered not in the age of Galileo, not even in the age of the first radio maps, but in the year 2020, within living memory, using data from a spacecraft still flying as I speak. And the wave is not the only large filament threading our arm. Branching away from the local arm runs another long, narrow feature, a great splinter of gas peeling off from the mainstream, which astronomers have only recently traced. To understand the texture of our arm, we should look at that split. Our arm, seen up close with the new tools, is not a simple, smooth stream. It has texture. It has branches and splinters, long, narrow features that peel away from the main body of the arm and run off at an angle. One of these has been mapped in detail in recent years, and astronomers have given it a plain and fitting name. They call it the split. To picture it, go back to the Massa surveys, the continent-sized radio eye measuring precise distances to the star-forming beacons across the galaxy. When Mark Reid, Yeshu, and their colleagues plotted the masses and the young stars belonging to our local arm, they did not find a single clean lane. They found that a long filament of gas and star-forming regions branches off from the main arm, splitting away and running between our arm and the next one inward, the Sagittarius arm. This branching filament, this great splinter, is the split. It is a feature thousands of light-years long, a kind of bridge or spur of its own, connecting the local arm toward its inner neighbour. This matters for a gentle but important reason. It tells us that spiral arms are not tidy, smooth, well-behaved lanes like the painted curves in a textbook diagram. Real arms are frayed. They have sub-branches, spurs, splinters and feathers, smaller features that jut off from the main flow at an angle. Astronomers studying other galaxies from the outside see exactly this kind of feathering in their arms, short perpendicular spurs branching off the main spiral, like barbs along the shaft of a feather. The split is one of our own arm's feathers, seen from the inside, trace star-forming region by star-forming region. There is something fitting in this, given where our story began. For decades our whole arm was dismissed as a mere spur, a minor branch. Now that we can see it properly, we find it is a substantial arm in its own right, and it has its own minor spurs branching off it. The structure repeats at smaller scales. The galaxy is built like that, with grand arms carrying lesser branches, and those branches carrying smaller wisps and clouds, down and down, the way a great river has tributaries, and the tributaries have streams, and the streams have trickles. It also reminds us how much of this is genuinely recent knowledge. The detailed shape of the split, the way it peels off the local arm, has been worked out only in the last decade or so, as the Massa distances and the Gaia parallaxes filled in the true three-dimensional layout of our neighbourhood. Earlier maps simply could not show it. The arm was a blur, and a blur has no feathers. Only when the depth came clear could we see that our home stream is braided and branching, with the split running off toward the inner galaxy. So the texture of our arm is intricate. There is the main body of the local arm, 20,000 light-years of it. There is the rippling Radcliffe Wave threading through the nearby part of it. There is the split branching off toward the Sagittarius arm, and studded all along it are the nurseries, the great clouds where new stars are being born right now. We have spoken of these nurseries in passing, naming the Orion Nebula again and again as the landmark our arm is named for. It is time to go there properly, to the brightest, nearest, most studied stellar nursery in our sky, and pin down just how far away it truly is. We keep returning to it, the smudge in the hunter's sword, the landmark that gave our whole arm its name. Now let us go there and look closely, because the Orion Nebula is not just a pretty patch of light. It is the nearest large stellar nursery to Earth, a place where stars are being born right now, and it is one of the most studied objects in all of astronomy. First, find it for yourself, because you can. On a clear winter night, look at the constellation Orion, find the 3 stars of the belt, and then look just below the belt for the short line of fainter stars that make the sword. The middle star of the sword is not a star. Even with the naked eye from a dark place it looks slightly fuzzy, a little soft. Through any small pair of binoculars it blooms into a misty glow. That glow is the Orion Nebula, a vast cloud of gas lit from within, and the light you're seeing left it centuries ago. How far away is it? This is the kind of number that earlier astronomers could only estimate roughly, but with the massa parallaxes and Gaia, it has now been pinned down with real precision. The Orion Nebula lies about 1,300 light-years from Earth. That means the light entering your eye tonight left the nebula around the year 700, when much of the world was in its early medieval age. You're seeing the nebula as it was more than 13 centuries ago. And on the scale of our 20,000 light-year arm, that distance, 1,300 light-years, is still very local. The Orion Nebula is practically next door, a nursery in our own part of the stream. Now picture what it actually is. The Orion Nebula is a great cloud of gas and dust, about 24 light-years across, glowing because it is lit from inside by a cluster of brilliant newborn stars. The gas glows the way the gas in a neon sign glows, energized by the fierce ultraviolet light of those hot young stars until it shines on its own. This is an emission nebula, a cloud made to glow by the young stars within it. And those stars are genuinely young, only 1 million or 2 years old, freshly made mere infants compared to our 4.5 billion-year-old sun. What makes the Orion Nebula so precious to astronomers is exactly this combination, that it is close, large, and actively making stars, all at once. It is the nearest place where we can watch high-mass star formation happening in detail. With telescopes, and especially with the Hubble Space Telescope, and now the James Webb Space Telescope, astronomers have peered into the nebula and seen the whole process laid bare. Dense knots of gas collapsing, newborn stars wrapped in their birth clouds, and around many of those young stars, flat disks of gas and dust where planets may be forming, the very kind of disk our own sun and planets once emerged from. So when you glance at that soft smudge in Orion's sword, you're looking at a stellar maternity ward 1,300 light-years away, a place where suns and perhaps future worlds are being assembled right now, in our own arm, on our own street. It is the brightest single proof that the Orion Arm is alive with starbirth, and the nebula we see glowing is only the bright face of something much larger and darker behind it, a giant cloud where the real work is hidden. To understand the nursery, we have to go inside. The glowing Orion Nebula that you can see is only the lit surface of something far larger and almost entirely hidden. Behind and around it lies a vast, dark, cold cloud of gas, hundreds of times bigger than the bright nebula itself, and invisible to the eye because it gives off no visible light. It is called the Orion Molecular Cloud, and it is the true nursery. The bright nebula is just the small patch where newborn stars have burned a glowing cavity into the near face of this enormous dark cloud. The word molecular is the key. In most of the thin gas between the stars, hydrogen exists as single, separate atoms. But in the densest, coldest, darkest clouds, the gas is packed tightly enough and shielded enough from starlight that atoms can join into molecules, 2 hydrogen atoms binding together, and many other molecules forming as well, including simple carbon compounds and even water. These molecular clouds are the coldest, densest places in the galaxy, often just a few degrees above the lowest possible temperature, and they are where, and only where, new stars are born. Gravity pulls the cold, dense gas together, knot by knot, until each knot collapses, heats, and ignites as a new star. The Orion molecular cloud is one of the nearest and most active of these great nurseries, stretching across hundreds of light years of our arm. It is not making one star at a time. It is making whole clusters of them, hundreds of stars forming together out of the same vast reservoir of gas. And right at the heart of the bright nebula sits the most famous of these newborn clusters, 4 brilliant young stars arranged in a tight little trapezoid shape. Astronomers call them the trapezium. The trapezium stars are the powerhouse of the whole visible nebula. They are massive, hot, and extremely young, and it is their fierce ultraviolet light pouring out in every direction that lights up the surrounding gas and makes the Orion Nebula glow. They are the lamps inside the lantern. Cluster around them, hidden in the gas, are many hundreds of fainter young stars, and around a great number of those young stars, astronomers have directly photographed small dark disks of gas and dust, silhouetted against the bright nebula behind them. These disks have a name, proplyds, short for protoplanetary disks, and they are nothing less than solar systems caught in the act of forming. Inside those flat spinning disks, planets are very likely coming together right now, the same way the Earth once did. This is the quiet marvel to hold on to. 1,300 light-years away, in our own arm, inside a cold, dark cloud we cannot see with our eyes, an entire generation of stars and their planets is being assembled. The Sun was born in exactly such a place, 4.5 billion years ago, in some long-dissolved molecular cloud, in a cluster of sibling stars that have long since drifted apart across the galaxy. When we look into the Orion molecular cloud, we are looking at our own origin, replayed, a picture of the kind of place that made us. The Orion Nebula and its dark mother cloud are the grandest landmark of our arm, but they are not the only ones. Scattered along the local arm near and far are other famous sites, a glittering cluster of young sisters, a vast complex of distant starbirth, and one swollen red giant that may, within our lifetime or not far beyond, give us the nearest supernova in centuries. Let us tour a few more landmarks of home. Our arm holds more famous sites than the Orion Nebula, and a short tour of a few of them shows how rich our local stream really is. Let us visit 3, each a different kind of landmark, all within the Orion Arm. Start with the Pleiades, one of the loveliest things in the night sky. Look toward the constellation Taurus on a winter evening, and you will find a small, tight little knot of stars like a tiny dipper that catches the eye at once. Most people can count 6 or 7 stars in it with the naked eye, which is why it's often called the Seven Sisters. Through binoculars, dozens more appear. The Pleiades are an open cluster, a group of stars all born together from the same cloud, still travelling together through space, and they lie about 440 light-years away. They are young as stars go, around 100 million years old, and they shine with a distinct blue-white colour because the brightest of them are hot young stars. They are a family of siblings, drifting through our arm together, much as the Sun's own birth siblings once did before they scattered. Now look the other way across the year, to the summer sky and the constellation Cygnus, the Swan, flying along the bright band of the Milky Way. In that direction lies one of the richest star-forming regions of our whole part of the galaxy, a vast complex of gas and young stars often called the Cygnus region. It is much farther than the Pleiades, more than 4,000 light-years away in places, and it is a powerhouse of starbirth, full of massive young stars, glowing gas and dark dust lanes. When you look towards Cygnus and see the Milky Way at its summer brightest, knotted and split by dark rifts, you're looking down a long, rich stretch of our own arm, layered with nurseries near and far. And finally, return to Orion, to the red shoulder of the hunter, the star Betelgeuse. We met it before as a marker of the constellation, but it deserves a closer look because it is a star living on the edge of its end. Betelgeuse is a red supergiant, an enormous, swollen, aging star perhaps 700 times the width of the Sun. If you placed it where the Sun is, its surface would swallow the orbits of the inner planets, reaching out past Mars. It is so large and so unstable that it visibly changes in brightness, and in late 2019 and early 2020 it dimmed dramatically, which set off worldwide speculation that it might be about to explode. It was not, as it turned out, just dimmed by a cloud of dust it had puffed out. But Betelgeuse is genuinely near the end of its life, and someday, certainly within the next 100,000 years and possibly much sooner, it will explode as a supernova. When it does, it will blaze in our sky as bright as the moon, visible even in daylight for weeks. It sits safely far away, around 500 to 600 light-years off, far too distant to harm us. It would simply be the most spectacular star our species has ever seen. These are only 3 landmarks of many. The point of the tour is the texture, the sense that our arm is not empty space but a living neighbourhood, full of clusters, nurseries and aging giants, each at its own distance, all carried along in the same great stream. And that stream itself is moving, carrying the Sun on a journey so long that one trip around defines a unit of time that dwarfs all human history. We have explored our arm as a place. Now let us feel it as a journey, because the Sun is not sitting still in the Orion Arm. It is orbiting the centre of the galaxy, carrying the Earth and everything on it, along a path so vast that a single loop takes longer than the entire history of complex life. We met the basic numbers earlier, but now we can let them open up. The Sun orbits the centre of the galaxy at about 230 kilometres every second. That is roughly 500,000 miles an hour. It is a speed that would carry you from the Earth to the Moon in about half an hour. And yet, moving that fast every second of every day, year after year, the Sun still takes somewhere between 225 and 250 million years to complete just one orbit around the galactic centre. That single immense loop is called a galactic year, or sometimes a cosmic year. Let the length of a galactic year settle in by comparing it to things you know. 1 galactic year ago, around 250 million years back, the Earth looked nothing like today. The continents were fused into a single great land mass, the supercontinent Pangaea. The dinosaurs had not yet risen to dominance. The great age of the dinosaurs, all of it, from their rise to the asteroid that ended them, fits inside a single galactic year, with time to spare. Since the Sun and Earth first formed, 4.5 billion years ago, the Sun has made only about 20 trips around the galaxy, 20 laps in the entire age of the solar system. Our star is, in galactic terms, barely 20 years old, and human history vanishes against this. In all the time since the first cities were built, perhaps 10,000 years, the Sun has travelled only about 1/5000th of the way around its current galactic orbit. The whole of recorded history, every empire, every life ever lived, every star anyone ever named, occupies a span in which the Sun has crept barely a single step along its enormous path through the Orion Arm. We are not only small in space, we are brief in this great motion, a single frame in a film that runs for 250 million years. The orbit is not a perfect circle either. The Sun's path is slightly oval, and it does not stay exactly in the flat mid-plane of the disk. As it orbits, the Sun also bobs gently up and down through the plane, rising a little above it, sinking a little below, crossing the mid-plane every 30 million years or so. like a horse on a carousel that rises and falls as it goes around. This bobbing is slow and gentle, carrying us only a few hundred light years above and below the plane, well within the thickness of the disk. But it means our motion through the arm is not a flat circle. It is a long, slow, rolling spiral of a path. So the Orion Arm is not a fixed address we hold forever. It is the stretch of road we're travelling along right now, on a journey measured in hundreds of millions of years. And because the arm itself is a density wave, moving at its own rate, the Sun and the arm do not keep perfect pace. We drift relative to the arm, slowly entering it, and, over vast spans of time, eventually leaving it. To understand our place fully, we have to look at that drift, at how the Sun moves through the very arm we call home. Here is a subtle and beautiful consequence of everything we have built so far. If a spiral arm is a density wave, a slow-moving pattern of crowding rather than a fixed bundle of stars, and if the Sun is orbiting the galaxy at its own speed, then the Sun and the arm are not locked together. They move at different rates. The Sun drifts through the arm. We are not permanent residents of the Orion Arm. We are passing through it. Let us picture this carefully, because it is easy to tangle. In most of the disk, the stars orbit the centre faster than the spiral pattern turns. So a star like the Sun gradually catches up to a spiral arm from behind, enters it, passes slowly through the crowded region, and eventually emerges out the front and pulls ahead, drifting on through the thinner space until, much later, it catches the next arm. The stars overtake the arms, the way cars on a highway catch up to and pass through a slow-moving zone of congestion that is itself creeping along the road. How long does a star spend inside an arm during one of these passages? The honest answer is that it depends on the details, on exactly how fast the arm pattern moves, which is itself uncertain, and astronomers give a range rather than a single clean number. But broadly, a star may spend on the order of tens of millions of years crossing through an arm, and then a longer stretch, perhaps 100 million years or more, travelling through the gap before reaching the next one. Over a single galactic year, 250 million years, the Sun may pass through an arm a few times. Across the whole life of the solar system, we have crossed through spiral arms many times over. This reframes the Orion Arm entirely. The gas around us, the bright young stars, the nurseries, the whole glowing identity of our arm, these are not the Sun's lifelong companions. They are the crowd we're among during this particular passage. When the Sun formed 4.5 billion years ago, it was in some other arm, some other crowd, long since left behind and itself long since reshaped. The stars that were our neighbours at birth have scattered all around the galaxy, and in the distant future, the Sun will leave the Orion Arm too and find itself among different stars in a different stretch of the Great Wheel. There is a question people naturally ask here, and it is worth addressing calmly. Does passing through a spiral arm endanger life on Earth? Inside an arm there are more massive stars and so more supernovae and more dense gas clouds. Some scientists have wondered whether our crossings into arms might line up with hard times in Earth's history, with ice ages or with mass extinctions, as the increased radiation or the passage through dense clouds disturbed our climate. It is an intriguing idea, and it has been studied, but the evidence is genuinely unsettled. The timing is hard to pin down, partly because we do not know the arm pattern's speed well enough, and most researchers think any such effect, if it exists at all, is modest. It is honest to say we simply do not know, and to leave it there, calmly, as an open question. What we can say is that right now, in this passage, our corner of the arm is quiet and our surroundings are mild, but that raises the next question. If we are drifting through, where are we headed, and will the Sun stay in the Orion Arm or leave it behind? If the Sun is drifting through the Orion Arm rather than fixed within it, then the natural question is the one any traveller asks. Where are we headed, and will we stay, or move on? The answer stretches our sense of time to its limit, and it comes wrapped in real uncertainty, which is worth being honest about. Start with what we know reasonably well. The Sun is currently somewhere within the Orion Arm, fairly well inside it rather than at an edge, and it is moving on its orbit around the galaxy. As we have seen, in most of the disk the stars orbit faster than the spiral pattern turns, so over time the Sun tends to drift forward through the arm and eventually out ahead of it. So the long-term expectation is yes, in time the Sun will leave the Orion Arm behind, emerge into the thinner space beyond it, cross a long gap, and much later encounter another arm. But now, the honesty. Exactly when this happens, and even the details of how, depend on a number we do not know well, the speed at which the spiral pattern itself turns. This is called the pattern speed, and it is one of the genuinely unsettled quantities in the study of our galaxy. Different methods give somewhat different answers, and the Orion Arm, being possibly a more complex feature than a clean density wave, makes it harder still. If the arm pattern moves at one speed, the Sun pulls ahead and exits in some tens of millions of years. If it moves at another, the timing shifts. Some studies even suggest the Sun's motion and the local arm's motion are unusually close, which would mean we linger in our arm far longer than a typical crossing. The truthful summary is that we will likely leave the Orion Arm eventually, but the timescale is uncertain, somewhere in the range of tens to hundreds of millions of years. Whatever the exact figure, the spans involved are so vast that they dwarf anything human. Tens of millions of years is far longer than our species has existed. Modern humans have been around for a few 100,000 years. The Sun will not noticeably change its place in the arm over all of recorded history, or over the entire future history we can sensibly imagine for civilization. On any human timescale, our address is utterly fixed. The drift through the arm matters on the scale of geology and evolution, not on the scale of empires or even of species. It is a truth about the deep future and the deep past, not about anything we will witness. It helps to hold both of these truths gently at once. On the one hand, our place in the arm is temporary, a passage, and over the long breath of galactic time the Sun wanders from one stretch of the wheel to another. On the other hand, that wandering is so slow that for every purpose that touches a human life, we are permanently, solidly, at home in the Orion Arm. Both are true. The arm is a passing crowd, and also the only neighbourhood we or any of our descendants for a very long time will ever know. And there is a reassuring fact woven through all of this drifting. Our particular corner of the galaxy, the region we have been crossing and will cross for ages, sits in a part of the disk that is unusually steady and calm, neither too crowded nor too barren, a quiet zone where a stable star like the Sun can shine for billions of years undisturbed. That calm is not an accident worth ignoring. It may be part of why we are here at all. There is a striking idea that ties our location to our very existence, and it is worth approaching slowly and carefully because it mixes solid fact with genuine speculation. The idea is that our particular place in the galaxy, far out in the disk, in the calm region we have been exploring, may be unusually well suited to life. Some scientists call the favourable region the galactic habitable zone. It is a real concept under active study, and also a debated one, so let us hold it honestly. Begin with the solid part. The galaxy is not the same everywhere, and some regions are genuinely more hazardous than others. Near the crowded centre, stars are packed far more densely. Supernovae go off more often, and the supermassive black hole and its surrounding violence flood the region with radiation. A planet there would be bathed every so often in bursts of intense radiation from nearby exploding stars and jostled by the gravity of passing stars. The very centre of the galaxy is a dangerous neighbourhood for delicate, long-lived chemistry like life. That much is not very controversial. At the same time, the far outer edges of the disk have a different problem. Out there, the gas from which stars and planets form contains fewer of the heavy elements, the carbon, oxygen, iron, and the rest, that are forged inside earlier generations of stars and that are needed to build rocky planets and living things. These heavy elements are more abundant toward the inner galaxy, where star formation has been busier and recycled more material, and they thin out toward the rim. so the very outskirts may struggle to build enough rocky planets at all. Between the dangerous, crowded, radiation-soaked centre and the metal-poor, planet-starved outskirts lies a more comfortable middle band, far enough out to be calm and safe, but not so far out that the raw materials for planets run thin. And the Sun, at about 26,000 light-years from the centre, sits comfortably within that favourable middle band. We're in the calm suburbs, with enough heavy elements to have built a rocky Earth, and far enough from the violent core to have been left in peace for the 4.5 billion years it took life to arise and evolve. Our position within the Orion Arm fits this calm picture too, because the Sun drifts through arms rather than sitting forever inside their most crowded, supernova-rich cores. We spend much of our time in the quieter gaps between the dense parts of arms, sheltered from the worst of the violence. Our long, gentle, nearly circular orbit keeps us from plunging toward the dangerous centre, or wandering out to the barren edge. The steadiness of our path is part of the steadiness of our home. Now the honest caveat, because this is where the science turns speculative. The galactic habitable zone is a useful idea, but it is not settled fact. Life might be more resilient than we assume, able to arise and survive in a wider range of galactic environments than the tidy zone suggests. The boundaries of the favourable region are fuzzy and debated, and we have only one example of an inhabited planet, our own, from which to reason. So we should hold this idea as a thoughtful possibility, not a proven law. It may be that our quiet corner is genuinely special. It may be that life finds a way in far rougher places. We do not yet know. What we do know is that our corner is in fact calm, and that calm has given life the long, undisturbed stretch of time it needed. And that calm is also what lets us look up at all, and try to understand the very arm that shelters us. Step back now, and consider something we have brushed against again and again throughout this journey, but never faced head-on. Everything we know about our galaxy, every map we have drawn, every distance we have measured, has been worked out from a single fixed seat inside the very thing we're trying to understand. We have never moved. We cannot move, not far enough to matter. Our entire science of the galaxy is the achievement of beings who looked outward from one small porch and reasoned out the shape of the whole house. This shapes what we can see in deep and specific ways. Because we sit inside the flat disk, the galaxy presents itself to us as a band, and the richest, most crowded directions toward the centre in Sagittarius are exactly the directions most blocked by dust. The very heart of our galaxy, the place we would most want to see, is the place most thoroughly hidden from ordinary view. We are like someone trying to understand the layout of a great forest while standing in a thicket with the densest, most interesting groves wrapped in the deepest mist. Our viewpoint hands us the hardest possible version of the problem, and yet, look at what has been wrung from that single seat. From this one fixed porch, by counting stars, William Herschel sketched the first shape of the galaxy. By measuring the swarm of globular clusters, Harlow Shapley moved us off the centre and found our true place in the suburbs. By listening to the faint radio whisper of hydrogen, astronomers traced the spiral arms through dust that no eye could pierce. By mapping the brilliant short-lived stars, they marked where the arms are forming new suns. By measuring the tiny yearly wobble of more than 1 billion stars, the Gaia spacecraft built a true three-dimensional chart of our neighbourhood. And by linking radio telescopes across a continent to catch the parallax of distant Marses, they pinned down the far structure of the arms and discovered that our own arm is no minor spur but a great branch 20,000 light-years long. Every one of these triumphs came from the same trapped position, the same inability to step outside. There is a quiet dignity in that, worth feeling on a clear night. We are small, and we are stuck, fixed to one moving grain in one arm of one galaxy among trillions. We will never see our galaxy whole, never get the photograph from outside, never look back at the Milky Way the way we look back at the Earth from the Moon. That view is forever denied to us, and still, from inside, we have measured the size of our arm, found the bubble we live in, traced the wave of gas running past us, weighed the black hole at the centre, and clocked our 500,000-mile-an-hour journey around a wheel 100,000 light-years wide. The map exists. We built it without ever leaving home. This is, in the end, the deepest meaning of being inside the Orion Arm. Our location is not just a fact about where we are. It is the lens through which we see everything, the source of both our blindness and our hard-won sight. The band of light overhead is not merely a thing we observe. It is the inside of our own address, the only view of home we will ever have, and we have learned to read it with extraordinary care. The reading is not finished. The map of our galaxy is still being drawn, still shifting with each new wave of data, and some of its most basic questions remain genuinely open. Before we return to the night sky, it is worth looking honestly at how much is still unknown. It would be a comfortable place to end, with our arm measured and our address filled in, as though the map of the Milky Way were finished and framed. But that is not the honest picture, and the honesty is part of the wonder. The map of our galaxy is still being drawn. Some of its most basic features are uncertain, debated, or only recently discovered, and the next decade will likely rewrite parts of what we think we know right now. Consider how many of the structures in this very story were unknown until recently. The true length of the Orion Arm, our own home, was established only in the 2010s, overturning 50 years of calling it a minor spur. The Radcliffe Wave, the largest coherent gas structure in our neighbourhood, running for 9,000 light-years right past us, was discovered in 2020. The detailed history of the local bubble we live inside was reconstructed only in 2022. The split, the great feather branching off our arm, was traced in the last decade or so. These are not ancient findings settled long ago. They are fresh, some of them younger than a child in school today, all made possible by the flood of new data from the Gaia spacecraft and the massa surveys. And the big questions remain genuinely open. We still do not know for certain how many major spiral arms the Milky Way has. For a long time, many astronomers favoured 4 major arms, but some infrared surveys suggested only 2 main arms, with the others being lesser features, and the matter is still discussed. We do not know the spiral pattern speed well, the pattern speed that governs how we drift through the arms. We do not fully understand why the Radcliffe Wave ripples as it does, or what set it oscillating. We do not know with confidence whether passages through spiral arms have shaped life's history on Earth. Even the exact distance to the galactic centre is refined and re-refined with each new measurement. The galaxy keeps its secrets, and we pry them loose slowly. There is a steady stream of new tools aimed at these questions. The Gaia spacecraft has released several great catalogues of star positions, each more precise than the last, and astronomers are still mining that treasure, with more to come. The James Webb Space Telescope peers into the dusty nurseries of our arm in infrared light, watching stars and planets form. New radio arrays continue to extend the massa distances. With each release of data, the map sharpens, structures appear that no one had seen, and old certainties are gently revised. The picture I've described tonight is the best we have right now, in this year. Some of it will look slightly different a decade from now, and that is not a weakness. It is the map breathing, growing, coming slowly into focus. This is worth carrying with you, because it changes how you might look up at the band of light. You're not looking at a solved thing, catalogued and closed. You're looking at an active frontier, a structure whose true shape is still emerging, measured a little more clearly every year by people patiently reading the sky from our one fixed seat inside it. The Orion Arm is both our oldest home and one of our newest discoveries, its real grandeur recognised only within living memory. So the map is still forming, drawn and redrawn from within. And with that humility in hand, we can return finally to where we began, to a dark field and a band of light overhead, and let the whole journey settle into a single quiet view. So let us go back to where we started, a dark field, far from any town. The night air cool and still. Your eyes adjusted now to the dark, and overhead, that faint band of light stretched across the sky, soft as smoke, the thing humans have looked at for as long as there have been humans, the Milky Way. Only now you know what you're looking at, and it is a different sky than the one you looked up at before. You know now that you're not looking at the band from the outside. You're inside it, seated in the flat disk of the galaxy, looking edge-on through the greatest depth of stars, which is why their gathered light piles up into a river across the dark. You know that the river is suns, hundreds of billions of them, too far to separate, just as Galileo first saw through his small telescope 4 centuries ago. You know that you sit far out toward the rim, 26,000 light-years from a hidden centre, in the calm suburbs, exactly where Harlow Shapley's globular clusters said you would be. And you know the name of your street, the Orion Arm. You can find its great landmark with your own eyes. Look for the hunter, find the 3 stars of his belt, drop down to the sword, and there, that faint smudge, is the Orion Nebula, a stellar nursery 1,300 light-years away, lit from within by newborn stars, making suns and perhaps worlds right now, in your own arm. You know that your arm is no minor spur, but a great branch of the galaxy, 20,000 light-years long, and that every single star you can see tonight, every named star in every constellation, fits inside one small lit corner of it. You know too that all of this is moving, the sun carrying you around the galaxy at 500,000 miles an hour, taking 250 million years to complete one loop. The arm itself a slow wave you're drifting through, the crowd of this passage, not the companions of forever. The bubble you sit inside, blown by ancient supernovae, the thin wisp of gas you're sailing through this very age, the great rippling wave of nurseries running past you, discovered only in your own lifetime, all of it in gentle, unhurried motion, and you along with it, riding the Orion Arm through the dark. And here is the quiet wonder to end on, the thing to carry back indoors with you. We have never once seen our galaxy whole. We never will. We're too small and too brief and too trapped inside it ever to step out and look back. And yet, from this one fixed seat, from this single dark field and millions like it, patient people have measured the size of our arm, mapped the bubble around us, weighed the black hole at our galaxy's heart, and traced the slow river of our own motion through the wheel. We cannot leave home, but we have learned, with extraordinary care, to read it. So the next time you find yourself under a truly dark sky, and that band of light appears, soft and uneven overhead, stay with it a moment longer than you would have before. That is not just a pretty smear across the night. That is the inside of your own address, the Orion Arm, seen the only way we will ever see it, from within. It is the largest thing you will ever be part of, and the closest. Look up, and you are looking at home.